Welcome back for more on Riemann Sums, and today we are going to get straight into it because last video went a little long. I apologize for that. And so last video we looked at finding the left rectangle approximation method. We're finding the area under this curve using left endpoint rectangles. So splitting it up into 4 rectangles and then using the left side of each interval to make a little rectangle. You probably guessed this already, but RRAM is the same idea except it's using the right endpoint. We're not actually going to do MRAM. I should probably spell correctly. Right. But MRAM uses the midpoint of each interval. It's actually the most accurate, but like I said in the last video, our goal is eventually to use an infinite amount of rectangles, and whenever we get to an infinite amount of rectangles, it doesn't even matter which we're using, left, right, or middle, and we'll see that on Monday. So let's get right into the right rectangles. So it's the same problem. I'm still trying to estimate the area under this curve from 0 to 4, and I'm still breaking it up into my 4 subintervals, except this time, instead of using the left side of each interval, I'm going to use the right side. So from 0 to 1, instead of going up from 0, I'm going to go up from 1 and then make my rectangle over. And we can see already this is going to be different than my first rectangle approximation method. For the next interval, I'm going to use, again, the right side, the 2 part of that interval from 1 to 2, and use that rectangle. From 2 to 3, I'll use going up to 3 and then over to make that rectangle. And then from 3 to 4, I'll use the right side 4, go up, draw my rectangle, and those are my 4 rectangles. So you can see on this particular curve, my right rectangles are going to be significantly taller than the actual area under the curve, whereas my left rectangles, pretty much all the rectangles were under the curve. My right rectangles will all be over the curve in this particular function. It might be good to ask yourself, is that always going to be true for each function? And the answer is no, it's not always true. It's just the way this curve is going up. So let's get right into it. The first rectangle, again, I'll call that rectangle A. The height of this rectangle is not from plugging in 0, it's now from plugging in 1. And if I plug in 1 into the function, I get 1 squared plus 4. 1 squared plus 4 is equal to 5. So the height is 5. The width of this rectangle remains 1. So the area is 5 times 1, or 5. My next rectangle, which I will use pink for. You might think I'm randomly picking the colors, but I'm strategically picking them, and I'll tell you why afterwards. The next rectangle comes from 1 to 2, and if I plug in 2, I will go up to the function. That will be the new height of the rectangle. So plugging in 2, 2 squared plus 4 is equal to 8. The width of this rectangle is still 1. And so the area is 8 times 1, or 8 for that pink rectangle. The next rectangle is this third rectangle, rectangle C. Again, I don't really care if you don't write the ABC. That's kind of an irrelevant part. I'm just doing it so in our notes we can make a reference to what we're doing. Especially if we're not using colors, it's easy to see that this rectangle C is the third rectangle. The height of this rectangle from 2 to 3, when I plug in 3 and go up, that gives me the height of the blue rectangle, so that comes from plugging in 3. And the height, when I plug in 3 squared plus 4, 9 plus 4 is indeed 13. The width of this rectangle is still 1, so the area is 13 times 1, which is 13. And lastly, I actually need a new color now. Use red, even though it looks similar to pink. My last rectangle, from 3 to 4, it's really plugging in the right side, or 4, going up till I hit the function, and that's the height of the rectangle. So plugging in 4 gives me the height of that last rectangle. Plugging in 4 squared, which is 16 plus 4 is equal to 20. The width of this rectangle has remained 1. 20 times 1 is 20. And if we add up all of those numbers, 5 plus 8 is 13, plus 13 is 26, plus 20 is 46. So using my left rectangles, I got an area of 30. Using my right rectangles, I got an area of 46. And you might wonder why I didn't show nearly as much work on this right RAM as I did on the left RAM, and that's because I'd actually already done a lot of that work already. Plugging in 1 to get 5, that's actually what I did over here, and that's actually why I kept the same color. These purple rectangles are actually the same height. Same thing with the pink rectangles, they're all just kind of shifted over. So with the left rectangles, I ended up plugging in 0, 1, 2, and 3. With the right rectangles, I ended up plugging in 1, 2, 3, and 4. And that's just based on me plugging in the right side of each interval. But 3 of those rectangles were exactly the same. The purple, the pink, and the blue were all coming from plugging in 1, 2, and 3. 1, 2, and 3. So that's why I didn't actually need to do a lot of this work in my head, because I had already done it over here. I already knew when I plugged in 1, I get out 5, etc. And you might be a little let down here, because we did all that work, and now all we know is that it's somewhere between 30 and 46. And I want you to stick with that discomfort for a little while with me. And let's try this last example for the day. And let's see what would happen if we used a smaller interval size. So instead of, I've sketched it below to save a little bit of time. You might want to pause the video to sketch it yourself. But instead of splitting this up into 4 intervals like we have been doing, let's double it. And so let's actually double the number of lines. Let's draw a line halfway down in between each one of those lines. So you can tell if I draw the rectangles in here, I will get hopefully a much more accurate area. I'll start doing it in color, but I'll probably get tired of that quickly. So if we set up our work over here, we're going to have a rectangle. We're going to calculate the height. We're going to calculate the width and the area. But this time we have a lot more rectangles. And I am going to do a significant amount of work quickly on my calculator on the side to save us some time going through this video and to keep track of the main idea in our head. So the first rectangle, I'm actually just using random colors again, is that rectangle there. It asked me to use the left rectangle, so again I went up from 0 for my first rectangle, and that'll be my first rectangle. So rectangle A, the height comes from when I plugged in 0 before. When I plug in 0 into that same function, I get out 4. You can look up at the example above to confirm that. This time though, my rectangles are not all having a width of 1. This rectangle goes from 0 to a half, so it's a width of 1/2. 4 times 1/2 is 2. And if we repeat this process for the next rectangle, using the left endpoint, means for that second rectangle, I'm plugging in a half into the function, which is not a nice thing to plug into a function. We're getting fractions and decimals. But when I plug in 1/2, I do get out 4.25. And the width of this rectangle remains 1/2. And when I multiply the length and width, 4.25 times 1/2, that's 2.125. So this is getting pretty decimally. We'll do one more, and then we'll kind of more quickly go through the rest of it. From 1 to 1.5 is my next interval. And if I'm drawing the left rectangle, that means I'm plugging in 1. So the third rectangle, I'm plugging in 1. And I will get, when I plug in 1, I already did that somewhere above, I get out 5. The width of this interval, the width of every interval, they're all going to be the same size interval. They're always going to be 1/2 because I'm just splitting up into smaller intervals. That creates an area of 5 times 1/2 or 2.5. Let's do one more just for kicks since I have one more color handy. From 1.5 to 2, if I go along the left side, that means I'm plugging in 1.5. When I plug in 1.5, I get out 6.25. The interval size remains 1/2, which is the width of the rectangle. When I do 6.25 times 1/2, I get 3.125. And as we try to think about filling in the rest of this, we're halfway there, so I could just keep going, but I'm going to try to go a little faster. I have 4 more rectangles. Let's see, we just did D, so we have E, F, G, and H. And the width of those rectangles, sorry about that shakiness, is always going to be 1/2. And it's really just plugging in the heights. So if I think about the remaining things that I have to plug in, I stopped at 1.5, which is this line right here. The next thing I'll plug in is 2. The next thing I'll plug in is 2.5. I keep going up. The next thing I'll plug in is 3. And the last thing I'm going to plug in is the last left side of the interval from 3.5 to 4. So the last thing I'm going to plug in is 3.5. And if you're doing this kind of quickly without thinking too much about it, you might be tempted to think, oh, I'm going from 0 to 4, so I should plug in 4 as the last thing. But no, if I'm using left rectangles, I will stop at the line before because that will be my last rectangle. I will never actually plug in 4 because if I plugged in 4, then I'd be drawing another rectangle that's not in the interval that it's asking about. So my last one will be 3.5. You can pause it if you want, but I'm going to quickly fill those in. When I plug in 2, I get out 8. When I plug in 2.5, I get out 10.25. When I plug in 3, I get out 13. And I plug in 3.5, I get out 16.25. If I cut each of those numbers in half, I get 4, 5.125, 6.5, and 8.125. And again, lots of tediousness there. Hopefully I saved you some of the effort of plugging it all into your calculator. Lots of room for error, obviously. And then I still need to plug in all these and add them all up. I encourage you to fact check me on this one. If you get a different answer, it doesn't mean you're wrong, because I did this pretty quickly on my own. I got a final answer of 33.5. Which, if we think about it relative to my other answers, I was expecting somewhere between 30 and 46. I was expecting a more accurate answer. And if I'm using smaller rectangles, I'm probably inching a little bit closer to the actual area. And so using the smaller rectangles gave me a better estimate. And we are going to pretty much stop there right now, but you guys are probably wondering, what is the actual area of that curve? Like, not the estimated area, but the actual area. And you can pause it right now if you guys want to guess as a class, but I'm just going to tell you. The actual area under the curve is equal to 37 1/3. How did I do that? Well, that is a topic for next week. We are going to find an infinite amount of rectangles next week. But don't worry, finding an infinite amount of rectangles doesn't mean that we're going to actually just keep doing more and more and more and more work. I don't think I'll have you do problems that are much more than 8 rectangles. And probably most of the problems on your homework tonight will continue to be 4 rectangles. So it's a lot of tediousness, but I think part of the joy is realizing what's ahead of us. So work hard on these examples, and I will see you next week to connect an infinite amount of rectangles along with sigma notation, and I'll leave you with Bernard Riemann. Have a wonderful day.